Hello everyone. Today we are going to do an experimental study of photoelectric effect. As you all know that this Leonard and R.M. Wilkins perform a extensive study on photoelectric effect. For that they perform an experiment in which they will use a evacuated glass tube having a photosensitive plate C and another metal plate A. In this figure, if you see that this C plate will represent the photo sensitive plate and A will represent the uh, metal plate, and this one is, as well represent the source of light, monochromatic source of light, which is instant on this quartz window, which only permits this ultraviolet light to incident on the plate C. Since plate C is a photosensitive plate, it will emit photoelectrons which move towards the plate A. As plate A has a positive charge, so it will attract the electrons, and this current start flowing through this circuit. The current flowing through this circuit is very small, and so it can be measured by a microammeter. This one is representing the microammeter. Now this one is a commutator which is used to change the polarity of these plates. If you see that this plate, photosensitive plate, will emit electrons, and plate A will collect these electrons. So C will represent the emitter plate and A will represent the collector plate. Now if you see this, the plate A can be maintained at a desired positive or negative potential with respect to the emitter plate. When the collector plate A is positive with respect to the emitter plate C, the electron are attracted to it, as I already told to you. The emission of electron causes flow of electric current in the circuit. This I already explained to you. Now the potential difference between the emitter and collector plate is measured by the voltmeter, which is given here. The photoelectric current can be increased or decreased by varying the potential of collector plate A with respect to the emitter plate C. This is the most important point, that photoelectric current can be increased or decreased by varying the potential of this collector plate A with respect to the emitter plate C. Now we are going to explain the effect of intensity of light on photocurrent on the basis of this experiment. Now if you are going to plot a graph between photoelectric current and intensity of light, we are getting a straight line there. Now the reason behind that, when a collector plate A is maintained at a positive potential with respect to emitter C, the electron ejected from the plate C are attracted towards the collector plate. Now if your frequency of the incident light and the potential are going to be fixed, the intensity of light is varied. How you can vary the intensity of the light? That can be varied by changing the distance of the light source and the emitter plate, so that we can change the intensity of the light on that basis. The resulting photoelectric current is measured each time. After varying the intensity of the light, we just going to measure the photoelectric current in every time, so that we can get a graph between this photoelectric current and the intensity of the light. Now it is found that if the photoelectric current increases linearly with the intensity of the incident light, as shown in the figure, the photocurrent is directly proportional to the number of photoelectrons emitted per second, which implies that the number of photoelectron emitted per second is directly proportional to the intensity of the incident radiation. Now we are going to discuss the effect of potential on photoelectric current. According to this experiment, we see that when a plate A here, if you see that plate A is at some positive potential with respect to the plate C, We find that when you are going to vary the positive potential of the plate A and simultaneously you measure the photoelectric current each time, you found that photoelectric current increases with the increase in positive potential of A. At some stage, for a certain positive potential of a plate A, all the emitted electrons are collected by this plate A, and the photoelectric current becomes maximum. If we increase the accelerating potential of a plate A further, the photoelectric current does not increase. The maximum value of photoelectric current is called saturation current. This maximum value of the photoelectric current is called, again I am telling you, that is a saturation current. Now, saturation current corresponds to the case when all the photoelectrons emitted by the emitter plate reaches the collector plate. That means all the electrons which is emitted from the this emitter plate are collected by the this collector plate. Now, now we are going to apply a negative potential to the plate A. What is going to be happen with respect to this plate C? Again, when you are going to apply a negative potential to the plate A, the electron coming from the emitter plate C are going to be repelled by the plate A because they have the same charge. Uh, the photoelectric current is found to be decreasing rapidly until it drops to a zero at certain uh, value, and this value of voltage is called, you can say that this cutoff voltage or cutoff potential or a stopping potential. Now, for a particular frequency of the incident radiation, a light, the minimum negative potential V naught given to the plate A for which the photocurrent stop or becomes zero is called again a cutoff or a stopping potential. The interpretation of this observation in terms of this photoelectric electrons is straightforward. All the photoelectrons emitted from the metal do not have the same energy. You must have to remember that all photoelectrons that are emitted from the metal do not have the same energy. The photoelectric current is zero when the stopping potential is sufficient to repel even the most energetic photoelectrons with the maximum kinetic energy. You always know that the photoelectric current must be zero when the stopping potential is sufficient to repel the most energetic photoelectron. That means that has a maximum kinetic energy. That electron possesses the maximum kinetic energy, that is K maximum, that is represented by K maximum, and is equal to EV naught. Now we can repeat this experiment for the incident radiation of same frequency but higher intensities, that is I2 and I3, that is given to you in this graph here. If you see that, then intensity is going to be increases, we getting the same stopping potential for each time. Uh, that is in the case of I1. For a given frequency of incident radiation, the stopping potential is incident of its intensity. Means the maximum kinetic energy of photoelectron depend on the light source and the emitter plate material, but is independent of the incident of the intensity of the incident radiation or light. You can say that. Here we are going to study the effect of frequency of incident radiation on stopping potential. For that, we are going to study the relation between the frequency nu of the incident radiation and the stopping potential V naught, or you can say that the negative potential V naught. If we suitably adjust the same intensity of light radiation at various frequencies and study the variation of this photoelectron with respect to the collector plate potential, the resulting variation is shown in this graph here. We obtain different values of stopping potential but the same value of saturation current for incident radiation of different frequency. The energy of this emitted electron depends on the frequency of the incident radiation. The stopping potential is more negative for higher frequencies of incident radiation. If you see in this graph here, if you see in this graph there, here we find out that the different values of stopping potential corresponding to different values of the this frequency of the incident radiations. As the frequency of the incident radiation is increases, the stopping potential is more negative, and you can see in this graph here that is more negative here, and this implies that the greater frequency of incident radiation or light, greater is the maximum kinetic energy of the photoelectron. Now if we plot a graph between this frequency of incident radiation and the corresponding stopping potential for different metals, we get a straight line as shown in this graph here. Now if you take two metals, photosensitive metals A and B, and their corresponding cutoff frequency is nu naught and nu naught dash, we find that certain minimum cutoff frequency nu naught for which the stopping potential is 0. That means that if you see that for this frequency nu naught for a metal A, the stopping potential is 0. Again for metal B, if you find that this cutoff for the cutoff frequency nu naught dash, the stopping potential again 0. Now from this graph we get some information here that the maximum energy of the photoelectron varies linearly with the frequency of the incident radiation, and this will represent that it is independent of the its intensity. Now a frequency nu of an incident radiation lower than cutoff frequency nu naught, in that case no photoelectron emission is possible. I'm talking about a general value of nu, that the nu which represent the frequency of the incident radiation which is lower than the cutoff frequency nu naught. In this figure if you see that this will represent nu naught, that is the cutoff frequency of this metal A, and nu is the general value here. If nu is the general value of the incident radiation is greater than the cutoff frequency of nu naught, then in that case photoelectron emission is possible, but below that there is no photo emission of electron is possible. Now this minimum cutoff frequency nu naught is called threshold frequency, and it is different for different metal. In graph if you see that the for metal A, that is cutoff frequency nu naught is there. This one, this nu naught is representing the cutoff frequency of this metal A, and this is also called a threshold frequency. And but for different metal B, the cutoff frequency is nu naught dash, it is represented by this. If you see that in graph also it is represented as nu and nu naught, that this will representing the cutoff frequency here, and so it is different for different metals. Now different photosensitive metal respond differently to the light, that is the most important point here. Now if you're talking about the selenium is more sensitive than zinc or copper. The same photosensitive substance give different response to light of different wavelength. For example, I'm talking about the ultraviolet light. In previous experiment we have discussed about that. When an ultraviolet light falls on a copper plate, the photoelectric effect is happened there. But when a green or red light falls on that copper plate, there is no kind of no such type of photoelectric emission is possible there. So this will shows that the same sensitive substance give different response to the light of different wavelength. I'm talking about the same photosensitive substance, that is copper here, and the different light of different wavelength is given as ultraviolet light and green light and red light. So I think so that it is clear to you. Thank you.